Okay, let's continue. Next, we will look at work equation by combining Newton's second law, and we have du equals to F times dr. From state 1 to 2, or point 1 to 2, we can do the integration to calculate work. And we can use F equals to ma to replace the F in the equation. Then we'll get the integration from 1 to 2 ma times dr. From chapter 1, we had this ADS equals to VdV. Hope you still remember. We will replace the A and R here, which is the acceleration and displacement is A and S in the ADS part, with the VdV. You see, after the integration, we'll get 1 over 2 m times v2 squared minus v1 squared. This really completes the last piece of puzzle here in this section. We talked about work, and we talked about work-related motion. Here we can officially give a name to this term. T, kinetic energy, equals to 1 over 2 times mass times velocity squared. And remember, this kinetic energy term is derived using Newton's second law. You put that F equals to ma, you replace F with ma into the work equation. So that's why we call the work and the kinetic energy. They're related. Based on the equation, T equals to 1 over 2 mv squared, we can see that it only depends on two things, mass and velocity. This is true because the change in kinetic energy is caused by work done on the particle or on the system, such as a free fall. If we look at from one state to another, we can calculate the difference in kinetic energy by taking the difference between T2 and T1. Alternatively, you can think this as initial kinetic energy with the addition of work done, either positive or negative, give you the final kinetic energy. There are many situations can benefit from using work and kinetic energy equations instead of just using the kinematics equations. When using kinetic energy equations, there is no need to know the acceleration and time. With a snapshot of initial and final velocity, we can calculate the force involved that did the work to change the velocity, or say, change the kinetic energy. The last two slides will cover the concept of power. I would like to use the velocity that we're familiar with to compare it. We already know that velocity is describing how quickly the displacement is changing. We can do ds over dt and unit in meter per second. Power, on the other hand, describes how quickly the work is done, or how quickly the work is changing. Or use du over dt, or u can be replaced as fdr over dt. Fdr over dt, dr over dt gives us the velocity, so eventually we got a force times velocity, fv. We can calculate power. And the unit is in joules per second. Well, maybe joule per second is the standard unit for power. However, in our daily life, you probably see watts or kilowatts or horsepower. These are more common power units that we use in our daily life. They can be converted to joules per second in these ways. When anything generates power, some part of the power generated will be lost, guaranteed. Right now, there's no way to have a 100% efficient power generating system because there's no perfect machine. All machines are subjected to power loss due to various reasons such as friction and many other factors. Therefore, we need to use a special equation to calculate the power efficiency, which is quite straightforward. The power output over the power input, measuring how effective your power is. Right? And M here stands for the mechanical efficiency. And EM, the power efficiency, has to be less than 1, has to be 100%. Right? The ideal case, when you're a super genius came up with a 100% effective machine, right? Cannot be over 100% because your output can never be greater than your input. Right? The best case scenario, your output equals to your input. That gives you EM equals to 1. but in our real life, EM always less than 1. I'll end here with a list of recommended readings. Thanks for watching. I'll see you next time.